The history of human populations has been shaped by several bottleneck events that drastically reduce their numbers. Bottlenecks in human history refer to periods when the human population drastically declined due to natural disasters, climate changes, or other catastrophic events, reducing genetic diversity and impacting evolutionary pathways. One of the significant bottlenecks is the early to middle Pleistocene transition, around 900 to 600,000 years. During this period, severe climatic fluctuations, including prolonged glacial cycles, may have reduced early human populations to extremely low numbers of up to 1,000 individuals in Europe. During the last glacial maximum 20,000 years ago, extreme cold and arid conditions during the peak of the Ice Age may have reduced habitable land and resources, leading to localized bottlenecks in human populations. Around 74,000 years ago, the Toba Super-eruption is believed to have caused a severe decline in global temperatures, impacting early human survival. Around 40,000 years ago, the Campanian Ignimbrite Eruption may have contributed to pressures on European and Asian populations and a significant Neanderthal population decline. More recently, around 12,900 years ago, the Younger Dryas event brought a sudden return to glacial conditions, affecting human settlements and migration. Around this time, the Neolithic transition led to the shift from hunter-gatherer societies to agriculture. The consequent population surges led to disease outbreaks and social upheavals that may have temporarily reduced population sizes. This video explores the evidence and impacts of these events on human evolution and survival.
Around 74,000 years ago, the Earth was beginning to emerge from one of its recent ice ages. While the ice reshaped much of the planet, the climates remained mostly steady in the tropical regions. A wide range of late Ice Age mammals inhabited the world, including the megafauna and some apex predators up in the cold regions of Eurasia. At this point, humans had spread across many parts of the Old World, although they had not yet reached Australia or the Americas. Most of the human population consisted of archaic Homo sapiens, who had first appeared in southern Africa about 300,000 years ago. By 74,000 years ago, these early humans had moved out of Africa and settled in much of Asia as well as parts of southeastern Europe. However, Europe was still dominated by another human species, the Neanderthals, who had adapted to life on the fringes of the northern ice sheets. Unlike Homo sapiens, Neanderthals were specifically adapted to conserve heat in cold climates. Denisovans, another early human species, was leaving its mark on the higher altitudes in Asia. Far to the east, early humans had spread throughout South and Southeast Asia. On the islands of Southeast Asia, including what is now Indonesia and the Philippines, Homo erectus had likely evolved into smaller species, such as Homo floresiensis and Homo luzonensis. These hobbits stood at just over 3 feet tall, shorter than any modern adult pygmies. As humans journeyed from Africa to settle in distant corners of the earth, they encountered a massive catastrophe, the eruption of Mount Toba, which drastically altered the ecological landscape of the time. Many scientists believe that this massive volcanic eruption caused a crash in the human population, referred to as the genetic bottleneck in the human population. A genetic bottleneck occurs when a population's size is dramatically reduced, typically due to a catastrophic event. This sharp decrease in population leads to a loss of genetic diversity. When the species recover from such an event, it does so from a small number of survivors, resulting in future populations having reduced genetic variability. Additionally, genes that were once rare in the species may become more common due to the limited genetic pool of the survivors. Over millions of years of Earth's history, volcanic activity has shaped its climate and evolution. Major volcanic eruptions during the last 3 million years have caused sharp drops in temperatures. These conclusions came from analyzing fossils found in deep-sea cores. During these cooler periods, drought-resistant plants expanded, showing significant changes in rainfall patterns. In the 1980s, fears of nuclear war between the USA and USSR led scientists to study nuclear winter, the potential global cooling effect of nuclear explosions. These studies revealed that a nuclear war could cause widespread famine due to massive crop failures. The climate models developed for nuclear winter studies were later applied to understanding large volcanic eruptions, like the massive Toba eruption 74,000 years ago. Researchers also examined historic eruptions like Krakatau, Tambora, and Pinatubo, which caused brief cooling effects lasting about a year or two. The Southeast Asia constitutes a volcanic island chain, which includes Sumatra, Java, and many smaller islands in the Malay archipelago. The islands are all formed from volcanoes, both active and ancient, and their dense tropical jungles are nourished by the rich volcanic soil, often making it difficult to recognize the presence of volcanoes beneath the lush vegetation. The Toba volcano, located in northern Sumatra, sits in an area with frequent earthquakes and volcanic activity. This is because it is near the Java subduction trench, where the Indo-Australian plate and the Sunda plate meet and push against each other. Toba is the largest volcanic crater or caldera from the last 2.6 million years, measuring about 100 kilometers long and 30 kilometers wide. Toba lies where two major geological fault lines, the Sumatran Fault and the Investigator Fracture Zone, meet, making the area highly unstable. Toba has erupted 4 times in the last million years. Its most powerful eruption about 74,000 years ago created the current caldera and deposited a thick volcanic layer called Younger Toba tuff, over 20,000 square kilometers, with ash spreading globally. The caldera is still uplifting, a process that may continue for hundreds of thousands of years before the next major eruption. Scientists have studied the ash from the massive Toba eruption, known as the youngest Toba tuff, using marine sediment cores, which are layers of mud and sand collected from the ocean floor that preserve Earth's history. Over 30 years ago, researchers found a widespread ash layer in cores from the Northeast Indian Ocean and Bay of Bengal. Research confirmed it came from Toba volcano, around 75,000 years old. This eruption coincided with a global climate shift from a warm interglacial to a colder glacial period. Later studies expanded the known range of youngest Toba tuff. The ash from Toba covered an area exceeding 10 million square kilometers, reaching as far as the Indian Ocean and South China Sea. The eruption was massive, with an ash volume of 20,000 square kilometers. The ash's spread indicates winds carried it both westward and eastward during the eruption, which lasted about 9 to 14 days and reached heights of at least 45 kilometers. In some ocean sediment cores, the ash layer is associated with a sharp cooling event confirmed by comparisons with Greenland ice core data. However, not all records show a clear temperature drop, possibly because the cooling was brief and difficult to detect in sediment layers that accumulate slowly. This underscores the complexity of reconstructing ancient climate impacts. The Toba eruption left volcanic ash, the youngest Toba tuff, across large parts of Asia. This ash was first noted on land in 1930 in Malaysia, where a thick layer covered older sand and gravel containing ancient stone tools. Chemical tests confirmed this ash came from Toba. Similar thick ash deposits were also found in Borneo, though their chemistry hasn't been analyzed yet. In India, volcanic ash linked to Toba was first found in the Sun Valley. Over time, researchers identified youngest Toba tuff in many parts of the Indian subcontinent, using advanced chemical analysis to confirm its origin. These studies also examined older Toba eruptions, like the Middle Toba tuff and Oldest Toba tuff, to distinguish them from the youngest Toba tuff. The youngest Toba tuff ash likely covered much of India soon after the eruption, forming a layer about 10 to 15 centimeters thick. However, natural erosion from rain and flowing water quickly removed much of this ash from hills and concentrated it in valleys, lakes, and rivers. This process is similar to what happened after the 1980 Mount St. Helens eruption in the US, where most ash was washed away within a few years. Scientists also debated the presence of older Toba ash in India. Some studies suggested it might exist in ancient deposits with early human tools, but this remains uncertain due to the reworking of the ash and tools over time. To confirm the origins of any Toba ash, researchers need precise chemical and dating methods. The youngest Toba tuff eruption occurred approximately 74,000 years ago, as confirmed by advanced dating techniques. This eruption ranks as one of Earth's largest known volcanic events, with a volcanic explosivity index of 8, categorizing it as a super-eruption. The eruption expelled approximately 2,800 cubic kilometers of volcanic material, far exceeding the output of historical eruptions like Tambora of 1815 and Krakatoa of 1883. The environmental impact of the youngest Toba tuff eruption was profound. It released massive amounts of sulfur, forming sulfuric acid aerosols that temporarily blocked sunlight. Estimates of sulfur released vary significantly, from 3.5 trillion to 330 trillion grams, but even the lower estimates imply considerable atmospheric disturbance. This reduction in sunlight could have ranged from conditions resembling an overcast day to levels barely sufficient for photosynthesis. These effects may have caused short-term global cooling, though the precise extent remains uncertain due to conflicting data. Volcanic eruptions, like the massive Toba Super-eruption, can have dramatic effects on the climate, both globally and locally. After an eruption, the release of sulfur into the atmosphere forms tiny droplets of sulfuric acid. These droplets act like mirrors, reflecting sunlight away from the Earth and causing a rapid cooling effect within a few months. Even smaller eruptions with high sulfur levels can cool the planet more than bigger eruptions with less sulfur. Scientists measure the impact of eruptions with something called the Dust Veil Index, or DVI, which shows how much volcanic dust is in the air and how long it stays. The Toba eruption had a DVI of about 3 lakh, which is thousands of times greater than the Krakatoa eruption of 1883. This means Toba's effects on temperatures and weather patterns were far more intense and lasted longer. While fine ash particles from Toba could have stayed in the air for years, larger ash particles fell back to the ground quickly, reducing some of the long-term impacts. One of the major ways volcanic eruptions affect the planet is by changing rainfall patterns. Volcanic dust has been linked to severe droughts, like those in Asia during the 17th and 18th centuries. Cooling caused by eruptions can weaken key weather systems, such as the Asian monsoon, leading to less rain and longer droughts. Cooler ocean surfaces after such eruptions can also cause less rainfall, and these effects can last for decades. Locally, volcanic ash can cause many problems. It can create a temporary condition called mock aridity, where plants struggle to grow because the ash blocks water from soaking into the soil, even in humid climates. The ash can also make soil and water more acidic, harming plants and animals for thousands of years. By reflecting sunlight, ash deposits temporarily cool the land and reduce rainfall, although this usually lasts only a few years. The Toba eruption is often compared to the idea of a nuclear winter, where ash and debris block sunlight, causing extreme global cooling. It likely played a role in ongoing climate shifts at the time, including colder temperatures, growing ice sheets, and falling sea levels. Some scientists believe Toba may have sped up the start of the last ice age, though others argue the cooling had already begun before the eruption. Toba's eruption may have cooled the northern hemisphere by about 3 degrees for several years, with some areas experiencing even more extreme drops. For example, summer temperatures in parts of Canada could have been 10 to 15 degrees lower for 2 or 3 years. Ice cores from places like Greenland show evidence of volcanic fallout, including a spike in sulfur that lasted 6 to 7.5 years, as well as colder conditions and increased dust levels. However, it's now believed the glaciation that followed was already underway before Toba erupted. The eruption also had far-reaching effects on ecosystems and early human populations. The extreme cooling and changes in weather would have devastated plants and crops, likely leading to widespread famine. Some researchers think this may have caused a sharp decline in early human numbers, contributing to a genetic bottleneck. Recent research confirms that Toba eruption had varying impacts on climate across different regions. In Africa and India, the cooling effect was less severe, with temperatures dropping by no more than 4 degrees. This milder cooling allowed human populations to continue their activities, challenging the idea of a catastrophic bottleneck. Rainfall decreased, but conditions remained mild in southern Africa, with no extreme freezing temperatures. Southern India saw forests persist longer than northern India, where cooler temperatures led to a shift from forests to grasslands. In Europe and Asia, the cooling was much more pronounced, with temperature drops reaching up to 10 degrees centigrade. These severe conditions likely contributed to the decline of Neanderthals in Europe and other early human species in Asia, as ecosystems became harsher and food sources more scarce. The cooling in these regions was significantly more disruptive than in Africa and India. The southern hemisphere experienced weaker cooling due to volcanic particles being concentrated in the northern hemisphere. Oceans also helped moderate the climate, preventing drastic temperature drops. This led to more stable conditions compared to the northern hemisphere. The Toba catastrophe model demonstrates a remarkable convergence of evidence from various scientific fields, uniting findings about volcanic events and human population history. Independent research into mitochondrial DNA from diverse human populations revealed signs of a significant population bottleneck around 70,000 years ago, followed by a rapid population expansion approximately 50,000 years ago. Subsequent reviews connected this genetic bottleneck to the Toba eruption, suggesting that the massive volcanic event may have played a key role in shaping the early history and recovery of modern human populations. In the context of human fossils, the bottleneck aligns with a weak Garden of Eden model of human evolution. This model suggests that modern humans originated in Africa, with groups migrating out at various times. The earliest migrant, Homo erectus, left Africa about 1.8 million years ago, reaching China and Java by 780,000 years ago, before disappearing around 70,000 years ago. Another archaic human relative, Homo heidelbergensis, emerged in Europe around 6 lakh years ago and disappeared approximately 3 lakh years ago. The fossil data indicates that the modern human lineage emerged in Africa around 3 lakh years ago. The African origin of modern humans during the Middle Pleistocene is supported by archaeological fossil and genetic evidences. Sites like Jebel Irhoud, Omo, and Herto provide insights into early modern Homo sapiens in Africa around 3 lakh years ago, displaying a mix of archaic and modern traits. These fossils represent transitional stages from archaic to modern Homo sapiens. During the Middle Pleistocene, early modern humans had a wide distribution across Africa, supporting the concept of African multi-regionalism. Fossils from different regions and within the same area showed diverse combinations of archaic and modern traits, indicating separate evolutionary paths. Fluctuating gene flow among small nomadic foraging groups contributed to this diversity. While the prevailing model suggests a rapid single-wave dispersal out of Africa, recent research proposes a more complex scenario. After their origin around 3 lakh years ago, several bands of humans made attempts to move out of Africa, but got fully successful only after 50 to 45,000 years ago. Before that, they were primarily restricted to Africa and neighboring parts of Southwest Asia like Levant. Outside of Africa, modern Homo sapien burials have been uncovered at the sites of Skul and Kafse in Israel, dated to between 90 to 130,000 years old, respectively. Similarly, the site of Jebel Faya in the United Arab Emirates contain tools that indicate Homo sapiens may have migrated here as early as 1 lakh 30 years ago too. About 600 kilometers away from Mount Carmel, a fossil from Al-Wasta in Saudi Arabia, represented by a single finger bone, overlaps with the time range of the Skul and Kafse fossils. Additionally, stone tools found throughout the Arabian Peninsula indicate human presence, although skeletal remains are scarce. After expanding out of Africa, modern Homo sapiens likely used 2 connections to the West Asia, one through the Sinai Peninsula to the Levant, Eastern Mediterranean, and another through the Southern Arabian Peninsula via the Straits of Bab el-Mandeb. Modern humans could have thrived along the southern coast of the Arabian Peninsula, utilizing resources and establishing routes towards South Asia. The fate of modern humans in the Levant after 90,000 years ago remains uncertain. Modern humans did not appear in the region until 45,000 years ago, and it is speculated that competition with Neanderthals may have played a role in the disappearance of modern human occupation. The Toba volcanic eruption is believed to have caused temporary cooling in potentially disrupted ecosystems, which could have indirectly influenced human populations. The main debate about the origins and migrations of modern humans centers on whether they migrated out of Africa into Asia before or after the Toba eruption. If humans reached Asia before the eruption, they likely were not the ancestors of modern humans, as they predate the bottleneck and disappeared, with post-Toba populations repopulating the world. Many researchers argue that humans spread to Eurasia only after the eruption, aligning with both archaeological evidence and genetic data. However, some archaeological sites in Asia claim to be over 75,000 years old, though their dating and connection to modern humans remain uncertain. Genetic studies, including those of mitochondrial and nuclear DNA, support the replacement hypothesis. These studies suggest that humans did indeed originate in Africa and then spread to other parts of the world around 1 lakh years ago. The bottleneck during the time made it unlikely for humans to have evolved gradually in different regions, as suggested the multi-regional theory. Additionally, the African human population is the genetically most diverse human population. Almost all present-day human genomic diversity can be traced to African populations. If humans had evolved separately in different regions, We would expect some unique genetic traits in these populations, but no such traits have been found. Between 6 lakh to 3 lakh years ago, the human population grew rapidly, especially in Africa, likely due to advancements in technology that allowed for better survival and resource use, leading to higher population densities. This growth and spread of humans from Africa supports the idea that modern humans replaced earlier populations. The timeline for the shift to modern human behavior is becoming clearer. Early signs of the later Stone Age are found in Kenya and Tanzania, dating back over 50,000 years. In places like Israel, the Sinai Peninsula, and Europe, the transition from the Middle Paleolithic to the Upper Paleolithic occurred around 46 to 42,000 years ago. This pattern supports the idea that modern humans and their technology originated in East Africa. However, it's unclear whether this cultural leap was directly linked to a population recovery after a genetic bottleneck. The timing of this bottleneck event in Africa is still debated. Typically, populations that survive bottlenecks have less genetic diversity, but Africa, being a large landmass, should have had the most diversity after the bottleneck. Studies show that Africa has about 3 times more genetic diversity than other regions. This raises the question of what caused these bottlenecks and why modern humans expanded afterwards. Toba Super-eruption is considered one possibility, which occurred around the same time as the bottleneck. The Toba Super-eruption was initially believed to have caused the extinction of hominins outside Africa, leaving only equatorial African populations to recolonize the rest of the world. This idea aligned with the out-of-Africa model, suggesting a replacement of global populations with modern humans originating from Africa after the eruption. Archaeological findings contradict the hypothesis of widespread extinction. In Sumatra and Malaysia, stone tools dated to the time of the eruption suggest local human survival. Similarly, in India's Juraru and Son river valleys, Middle Paleolithic tools before and after the eruption show continuity in human activity. China also exhibits uninterrupted cultural and technological traditions, with no evidence of a population hiatus due to Toba. Discoveries like modern human teeth in Fuyan Cave, China, dating 120 to 80,000 years ago, demonstrate that modern humans were already present in Asia before the eruption. This undermines claims that post-Toba migrants from Africa replaced existing populations. Archaic hominins such as Neanderthals, Denisovans, Homo floresiensis, and Homo luzonensis survived across Eurasia during the same period, even in regions near the Toba crater. Their continued existence further refutes the notion of complete extinction caused by the eruption. As geologists refined the Toba eruption model and geneticists examined the timing of genetic changes in humans, additional evidence of population bottlenecks emerged from diverse sources, strengthening the case for a global impact. Research on various species revealed similar patterns of population reduction and recovery around the time of the Toba eruption. In 2004, DNA analysis of tiger subspecies showed a severe bottleneck about 72,000 years ago, aligning with human timelines. Further studies in 2014 revealed widespread bottlenecks in Southeast Asian cat populations, including cheetahs, around the same period. Similarly, DNA sequencing of giant pandas in 2012 found evidence of significant population fluctuations, with a major bottleneck occurring before 50,000 years ago. Primate studies echoed these findings. Orangutans experienced a bottleneck and subsequent expansion around 64,000 years ago, while macaques in South Asia faced a bottleneck coinciding with or shortly after the Toba event. Even in Africa, gorillas and chimpanzees showed signs of population crashes around 70,000 years ago, with gorilla populations estimated to have dropped to about 29,000 mated pairs. Surprisingly, even bacteria reveal clues to this ancient event. Helicobacter pylori, a gut bacterium found in over half of humans, traces its spread from African ancestors to Eurasian populations to before 58,000 years ago, just after the Toba eruption and human population expansion. These patterns are consistent across many sequenced genomes of organisms with Eurasian ancestors from 70,000 years ago, showing bottlenecks followed by population recoveries about 50,000 years ago. While most research focuses on prominent species, untapped genomes may hold further surprises, offering even more insights into the far-reaching impacts of the Toba eruption. Analysis of eastern chimpanzees' mitochondrial DNA shows a population decline around the same time as humans, suggesting a global environmental catastrophe likely triggered by Toba's eruption. Some chimpanzee populations, in particular areas of Uganda and Zaire, went through a bottleneck around 67,000 years ago. Other populations in more exposed areas may have been affected by climate changes during the last glacial maximum about 20,000 years ago. Volcanic eruptions rich in sulfur can cause global cooling, but Toba's eruption was different. While eruptions like Toba's are explosive, they emit fewer sulfur aerosols, making their cooling effects less immediate, but potentially longer lasting. Climate models and ice core data suggest that Toba's eruption caused rapid cooling over the first few years, followed by a cooling period lasting decades and even centuries. This cooling could have led to reduced precipitation and affected ecosystems globally. In southern Africa, there is no evidence of disruption in human activity during or after the eruption. Similarly, terrestrial mammals in Southeast Asia, including humans, appear to have endured the environmental effects with limited impact, showing resilience against the Toba event. The Toba Super-eruption's climatic impact was significantly influenced by the type and quantity of sulfur aerosols released. Research indicates that the eruption might have produced smaller aerosol particles or released a lower amount of sulfuric acid aerosols, which could have limited the magnitude of cooling. This would result in a milder volcanic winter comparable to modern eruptions such as Mount Pinatubo, where cooling effects were temporary and not as extreme. Water vapor emissions during the eruption were crucial in mitigating its impact. Water vapor is far more abundant in volcanic gases than sulfur dioxide and has a warming effect on the atmosphere. By increasing global warming, water vapor could have counterbalanced the cooling effects of volcanic aerosols, leading to a less severe climatic disruption. Simulations that incorporate water vapor emissions show limited environmental impacts, further supporting this view. Solar insolation, Earth's principal energy source, was higher around 74,000 years ago than today due to orbital configurations. These conditions allowed for faster recovery from the cooling period. Additionally, orbital factors created seasonal patterns that could have facilitated human survival, such as colder springs, warmer autumns, and less extreme temperature differences between summer and winter. The volcanic eruption likely caused immediate northern hemisphere summer cooling, but simultaneous winter warming. This would have minimized global temperature drops in the initial years after the eruption. Such seasonal adjustments could have enabled ancient humans to adapt to the changing climate or migrate to less affected regions, enhancing their chances of survival. The Toba Super-eruption caused significant destruction to local environments and influenced global weather patterns. However, high-resolution geological records suggest that the climate and ecosystems recovered within a few years, avoiding long-term global devastation. Archaeological evidence shows continuous human activity before and after the eruption, even in heavily ash-affected regions like India and Sumatra, highlighting ancient humans' adaptability to environmental changes. Genetic analyses of archaic humans, such as Neanderthals, Denisovans, and species like Homo floresiensis and Homo luzonensis, further confirm their survival during and after the Toba event. This evidence challenges the hypothesis that the eruption caused widespread human extinction and a severe population bottleneck. While the idea of Toba's catastrophic global impact offers a simplistic explanation for complex phenomena, it ignores critical factors in Earth's systems and human adaptability. Current data demonstrate that the influence of the Toba eruption on global climate, ecosystems, and ancient human populations was significantly overestimated. It is now necessary to adopt a more nuanced and evidence-based perspective on paleoclimatic changes and human evolution, moving beyond outdated, catastrophic interpretations. During the last ice age between 130,000 years ago, anatomically modern humans migrated out of Africa into Europe, where they encountered the indigenous Neanderthals. Neanderthal populations began to decline around 60,000 years ago and had largely disappeared by 40,000 years ago. This period was marked by dramatic climate fluctuations in Europe, swinging between freezing Heinrich events and warmer interstadial periods. During the cold spells, early human species were pushed out of northern Europe, retreating to southern refuges like the Iberian Peninsula. When the climate warmed, they returned to the north. Over time, these humans developed more advanced tools, created intricate ornaments and ritual objects, and strengthened their social networks, signifying a shift from Middle to Upper Paleolithic cultures. In Europe, Upper Paleolithic cultures, such as the Aurignacian, are generally associated with modern humans, whereas Neanderthals are linked to Middle Paleolithic cultures. The transition from Middle to Upper Paleolithic industries is considered one of the most significant milestones in prehistory. This change is analyzed in two ways: biological change, focusing on the physical and genetic differences between Neanderthals and modern humans, and cultural change, examining advancements in tools and artifacts. Traditionally, archaeologists viewed this shift as a sudden leap, with new technologies and behaviors appearing abruptly around 40,000 years ago. However, it remains unclear whether these changes were primarily driven by sudden climatic shifts that tested human survival skills. Some believe that climate change played a central role in the Neanderthals' extinction. It may have gradually worn down their populations during colder periods or triggered a sudden collapse during a particularly harsh Heinrich event around 48,000 years ago. Others argue that climate alone cannot explain their demise, as Neanderthals had previously endured similar fluctuations. Alternative explanations include conflict or displacement by modern humans, or the environmental aftermath of the Campanian Ignimbrite volcanic eruption around 40,000 years ago. This volcanic eruption, one of the largest in Europe's history, likely caused a volcanic winter that worsened conditions during an already cold period. Some theories suggest that this event forced Neanderthals out of key regions or created conditions that favored the spread of modern humans. Scientists are now better equipped to investigate such events, thanks to the discovery of microscopic volcanic ash particles, or cryptotephra, which provide precise time markers to synchronize cultural and environmental records. While uncertainties remain, these advances are shedding light on how climatic and environmental factors intersected with human history to shape the prehistoric world. 40,000 years ago, the Campanian Ignimbrite Eruption struck southern Italy, near the Bay of Naples. This super-eruption is one of the most powerful in the Northern Hemisphere over the last 200,000 years. The eruption originated from the Phlegrean Fields, a massive supervolcanic caldera near the Bay of Naples in southern Italy. This geologically active region is characterized by numerous craters, hot springs, and fumaroles, and it has been a site of significant volcanic activity for hundreds of thousands of years. The Campanian Ignimbrite Eruption released vast amounts of volcanic ash, pumice, and gases into the atmosphere, reshaping both the regional and global climate. Its environmental consequences are evident in archaeological records from southern and eastern Europe, showing its influence on hunter-gatherer lifeways. During the Campanian Ignimbrite Eruption, Europe experienced a period of shifting cultures and populations. The warmer climate during the Hengelo Interstatal, a brief warm period that lasted from 41,000 to 38,000 years ago, helped human groups survive and thrive. They developed better tools, ate a wider variety of foods, and moved across vast areas with diverse environments, adapting well to their surroundings. A Campanian Ignimbrite eruption unfolded in two dramatic stages. The first stage was an ultra-explosive phase, where volcanic ash, gases, and rock fragments were blasted into the atmosphere, forming a towering column that reached up to 44 kilometers high. In the second stage, the ground around the volcanic vent collapsed, creating a massive caldera, or volcanic crater. This collapse triggered pyroclastic flows, fast-moving avalanches of superheated gas, ash, and volcanic debris that sped across the land at hundreds of kilometers per hour, scorching everything in their path. These flows extended as far as 80 kilometers from the eruption site, devastating the surrounding region. The eruption's impact extended far beyond the local area. The ash and debris ejected during the event spread over an astonishing area of at least 5 million square kilometers, blanketing parts of Europe, the Mediterranean, and beyond. The eruption had widespread environmental and cultural impacts, especially in the greater Mediterranean region, covering areas like southern Italy, southeastern Europe, parts of Anatolia, and the East European plain. The eruption's sulfur emissions amplified atmospheric effects, likely causing a volcanic winter with severe ecological disruptions. The Campanian Ignimbrite Eruption coincided with several important events in Earth's history. It happened during a major cooling period known as Heinrich Event 4, when vast amounts of icebergs broke off into the North Atlantic, disrupting ocean currents and cooling the climate. At the same time, Earth's magnetic field temporarily weakened, an event known as the Longchamp excursion. These connections were established by studying volcanic ash layers, called tephra, found in Greenland ice cores, and using precise dating techniques, which confirmed the eruption occurred around 40,000 years ago. The eruption caused profound climatic effects by releasing an enormous amount of sulfur gas into the atmosphere, up to 2 quadrillion grams. Once in the stratosphere, these sulfur gases formed aerosols, tiny particles that reflect sunlight away from Earth, causing global temperatures to drop. Scientists estimate that this event triggered a temperature decline of 3 to 4 degrees, with cooling effects lasting 2 to 3 years. But the eruption's impact didn't stop with short-term cooling. It coincided with a highly unstable period during the last glacial period, amplifying ongoing climate disruptions. The sulfur aerosols and ash from the eruption likely caused a prolonged volcanic winter, a period of extreme cold that persisted for decades or even centuries. This harsh climate made survival more challenging for ecosystems and human populations across the northern hemisphere. While the ashfall primarily blanketed areas close to the eruption, its climatic effects were felt far beyond, particularly in Europe and Asia. The cooling, combined with the pre-existing glacial conditions, likely disrupted food chains, habitats, and human migration patterns. The eruption remains a striking example of how volcanic activity can influence both local landscapes and the global climate for centuries. The impact of the Campanian Ignimbrite eruption was particularly harsh in the already cold and fragile glacial environment. The volcanic winter due to the eruption was magnified because the Earth was already in a glacial period. In large parts of Europe and the Mediterranean, this cooling caused ecosystems to drastically change. Forests may have shrunk, grasslands expanded, and many species of plants and animals struggled to survive. For humans, these environmental changes could have been devastating, forcing some groups to abandon their homes and adapt to new survival strategies. The Ignimbrite eruption didn't just affect the land and climate, disrupting the ocean and atmosphere systems. This created long-lasting environmental shifts that likely influenced where and how ancient human populations lived. Archaeological evidence suggests that these changes were particularly severe in regions like Iberia, which includes modern-day Spain and Portugal. The eruption is not just a monumental volcanic event. It's a crucial marker in archaeology. Its widespread ash deposits, found across Western Eurasia, help scientists understand ancient timelines. These layers, called tephra, are like timestamps in the earth, sealing archaeological sites and separating earlier cultures from later ones. For example, in southern Italy, the volcanic deposits include two main parts: a lower layer of Plinian pumice, which is light volcanic rock from explosive eruptions, and an upper layer of ignimbrite, solidified material from pyroclastic flows. Together, these layers separate early Upper Paleolithic cultures, like those with Aurignacian-like tools, from later Gravettian cultures with different toolmaking styles. In Eastern Europe, the Campanian Ignimbrite ash is identified by its unique chemical makeup, making it a reliable marker for archaeologists. In Europe, the Upper Paleolithic cultures appear after the Campanian Ignimbrite eruption. However, some archaeological evidence suggests that these Upper Paleolithic cultures could be older than 40,000 years. Neanderthals are known to have lived in Europe after the eruption, particularly in the Iberian Peninsula. But the end of Middle Paleolithic industries at certain Eastern European sites occurred well before the eruption. In Italy, several sites show that modern humans were present before this eruption, as Upper Paleolithic deposits are found below its ash layer. In the southern Balkans, like Montenegro and Greece, the eruption covers Middle Paleolithic layers. But in other areas like Bulgaria, Serbia, and Macedonia, it overlaps with early Upper Paleolithic layers, suggesting modern humans were already present before the eruption. Early Upper Paleolithic layers in Russia are found below or within the Campanian Ignimbrite ash, supporting the idea that modern humans were already in central Russia before the eruption. The Campanian Ignimbrite ash has been traced as far as Libya, helping to link Paleolithic records between Europe and Africa. At Hawaftea Cave in Libya, the Campanian Ignimbrite appears above Middle Paleolithic industries and modern human remains, showing humans were present before the eruption. Early modern humans were also present in Morocco over 100,000 years ago, and in Egypt, they lived well before the Campanian Ignimbrite eruption, with no signs of the eruption impacting their activities. Tracing the Campanian Ignimbrite ash at various sites in Eastern Europe has provided a reference point for understanding the timing of modern human industries and migrations. Some sites recorded Aurignacian-type industries much earlier than others. New dating techniques are revealing that modern humans were in parts of Europe earlier than previously thought, and using the Campanian Ignimbrite ash as a reference helps confirm these findings, providing a reliable timeline for human migrations and cultural developments across Europe and Africa. The transition from Middle to Upper Paleolithic cultures began before the eruption, both in North Africa and Europe. This suggests that neither the eruption nor the cold period during Heinrich Event 4 were the main causes of cultural changes, population movements, or Neanderthal extinction in Northern and Eastern Europe. Neanderthals and early modern humans were likely more resilient to environmental crises than previously believed. A study of Neanderthal mitochondrial DNA suggests that Neanderthal populations in Eastern Europe continued until their extinction, likely long before the eruption. The impact of the eruption varied depending on proximity to the volcanic source. Sites near Campi Flegrei like Serino were heavily impacted, with a thick Campanian Ignimbrite ash layer capping early Aurignacian deposits and no evidence of reoccupation. However, deposits found farther from the eruption source suggest less severe effects, with no evidence of widespread, long-term impacts on human populations. The evidence suggests that Neanderthal extinction in Europe wasn't directly linked to the eruption. Continuous records of human occupation during the Middle to Upper Paleolithic transition raise doubts about the extent of cooling effects from He4 on Neanderthal extinction. Modern humans were already widespread in Europe before the eruption, meaning that Neanderthals and modern humans interacted before 40,000 years ago. Modern humans, with their small populations and high mobility, were likely a greater threat to Neanderthals than the eruption, or climate cooling, ultimately leading to the Neanderthals' extinction. While the extinction of Neanderthals is difficult to be attributed to the eruption, some human groups might have found ways to adapt, while others couldn't cope with the extreme conditions. This could have created situations where certain groups of early humans gained advantages over others, shaping the course of human evolution and migration. For example, groups that developed better tools or found ways to use scarce resources more effectively may have been more likely to survive and spread. The combined effects of the Campanian Ignimbrite Eruption and the harsh climate of Heinrich Event 4 significantly impacted Paleolithic people in Western Eurasia. The volcanic eruption, along with the cooling climate, forced humans to adapt, influencing their movement, settlement patterns, and cultural development. In areas directly affected by volcanic fallout, like the Mediterranean and parts of Eastern Europe, many human settlements were abandoned. These disruptions suggest that the eruption caused a major shift in how people lived, with new patterns of land use emerging when humans returned, even though cultural practices may not have changed drastically. Human mobility was also influenced by the environmental changes. During this time, the availability of habitable land decreased by up to 30%, which likely led to shifts in population distribution and new settlement strategies. In regions like Turkey and the Caucasus, evidence points to changes in habitation, suggesting that the cooling from the eruption and climatic shifts were felt over a wide area. These changes would have altered how hunter-gatherer societies moved, lived, and interacted as they adapted to the challenging environmental conditions. The eruption and cooling also had a profound impact on technology and culture. As resources became scarcer, people developed more efficient tools and new technologies to cope with the changing environment. Tools became smaller, more precise, and often made from a wider range of materials, such as bone and antler. There was also an increase in the use of composite tools, like hafted stone tools, and a growing interest in personal adornment and art, signaling cultural shifts. These innovations were a direct response to the stress caused by volcanic eruption and climate change, allowing humans to adapt to new challenges. Environmental crises played a significant role in reshaping societal structures and ideologies. Human displacement was a predictable outcome as groups moved away from heavily impacted regions to seek better living conditions. This movement led to two major regional consequences: depopulation in some areas and crowding in others. Depopulation resulted from uninhabitable conditions, while crowding occurred in less affected or fringe areas, intensifying social pressures and fostering innovative behaviors within and between groups. The displacement forced human groups to adapt to unfamiliar landscapes, triggering both challenges and opportunities. Socially constructed cognition, which links specific locations to meaning and association, played a critical role in this adaptation. This process heightened both social fragility and resilience. Increased population densities, particularly in crowded settings, fostered intensified social interactions. As a result, cultural expressions like personal adornment and symbolic practices gained importance, helping individuals and groups establish identities and maintain cohesion under challenging circumstances. Art and symbolic expression were adaptive responses to the pressures of displacement and crowding. Items like pendants and beads became more socially significant, reflecting the need for identity formation and intergroup communication. Image-making, often viewed as a hallmark of modern behavior, was instead a response to sociogenic factors, such as heightened social networking needs and increased population density. Art served practical functions, including cultural transmission and fostering collective emotions during periods of stress. The crisis caused widespread population displacement, creating a mosaic of depopulated and overcrowded regions. These demographic changes altered social dynamics, reducing group sizes in some areas while increasing density in others. Such shifts imposed cognitive and social stresses, leading to the evolution of new behaviors and interactions. These challenges likely drove innovation in communication, cooperation, and social structures. While the abrupt environmental changes were challenging, they also acted as catalysts for societal innovation. The crisis accelerated the adoption of new behaviors and tools, some of which became foundational for later Upper Paleolithic traditions. This period marked a shift toward more complex societal structures, driven by the need for flexibility and resilience in the face of adversity. The crisis prompted a form of selection at the population and behavioral levels, where successful innovations enhanced survival. Behaviors promoting mutual benefits and reciprocal relationships were more likely to succeed. Conversely, groups or behaviors that failed to adapt effectively disappeared from the archaeological record. This selective process underscores the evolutionary significance of cooperation and adaptability. Under sustained stress, innovation and flexibility became paramount. Women and young adults emerged as pivotal social drivers, shaping the division of labor and fostering adaptive strategies. Their roles in the evolutionary trajectory of Paleolithic societies highlight the importance of inclusive contributions to resilience and survival during times of profound environmental and societal change. The resilience of human societies in the face of environmental crises is a key consideration. Although the crisis imposed significant pressures, humans displayed remarkable adaptability. While such catastrophes often have short-term impacts, humans' inherent ability to adapt ensures survival, even if selectively. The crisis accelerated ongoing innovations, favoring resilient groups and leading to significant cultural shifts. The crisis caused by the twin events of Campanian Ignimbrite Eruption and Heinrich Event 4 acted as a strong selective pressure, advancing human societies through descent with rapid modification. Maladaptive and rigid groups were disadvantaged, while innovative and flexible ones thrived. This resilience is evident in the transition from Middle Paleolithic groups to new cultural expressions like the late Mousterian and Aurignacian traditions. These shifts emerged after a period of repopulation and adaptation. Comparisons to other volcanic events like the Toba Super-eruption, which happened around 74,000 years ago, and the Younger Dryas eruption around 13,000 years ago, reveal differences in impacts. The Toba eruption's effects on human populations remain debated, as evidence suggests regional persistence despite its magnitude. In contrast, the Younger Dryas eruption in western Germany triggered widespread demographic and cultural changes, including technological innovations and regional depopulation. The environmental and climatic contexts of eruptions influence their impacts. For example, the Campanian Ignimbrite Eruption occurred in a glacial period, with widespread ashfall over land, and affecting ecosystems and human groups differently than equatorial eruptions like Toba. These conditions led to significant disruptions, including population relocation, technological shifts, and cultural reorganization. Overall, these events underscore the resilience of human societies. Humans adapted through innovation, social reorganization, and cultural evolution despite environmental challenges. These crises, while disruptive, often served as catalysts for long-term progress and transformation in human history. Current hunter-gatherer groups offer limited insights since their environmental and cultural conditions differ significantly from those of the last glacial period. However, studies from regions like Southeast Asia and Siberia provide clues about how volcanic events affected early societies. Catastrophic events like volcanic eruptions often remain in collective memory for thousands of years. For example, Aboriginal stories of Mount Gambier and legends from Papua New Guinea recall such events in remarkable detail. These memories highlight the long-term cognitive impacts of disasters, which may also have archaeological significance in Paleolithic studies. Success in adapting to environmental changes often depends on resource diversification rather than inherent superiority. Some groups may have thrived during the crises by adopting more flexible subsistence strategies. This challenges simple models of population replacement and emphasizes the importance of adaptation. Cultural changes during this period were more about local adaptation than sudden migrations or colonizations. Environmental pressures, like the crises evented in our conversation, accelerated the evolution of existing cultural traits within Middle Paleolithic societies, leading to gradual transitions rather than abrupt shifts. The event acted as a catalyst, bringing out cultural traits that were already present. Under stress, these traits became more significant, leading to the diversification and specialization of traditions like the Mousterian. This process reflects change within continuity rather than abrupt transitions. The crises may have influenced human evolution by causing population bottlenecks and genetic mixing. While it might have indirectly impacted anatomical changes, its precise role remains unclear and requires further research. In summary, the eruption event prompted gradual cultural and biological evolution by acting as a stressor and catalyst for change. Its effects were complex, challenging simplistic theories of abrupt replacements or migrations. As the Ice Age drew to a close, the world was on the cusp of dramatic transformation, and so too were the humans who had roamed it for millennia. By the time of the Younger Dryas, humans had spread far and wide, from the icy tundras of the Americas to the sun-baked plains of Australia, carving out lives across every corner of the earth. This sudden, harsh cold snap posed a new set of challenges for these resilient hunter-gatherers. Far from stalling human progress, the Younger Dryas ignited new strategies, forcing early societies to innovate and adapt. As the world's landscapes shifted, so too did the dynamics of human survival. From the icy reindeer hunts of northern Europe to the strategic fishing in the southern regions, the end of the Ice Age tested human ingenuity like never before. This critical period not only shaped the way humans interacted with their environments, but also paved the way for the rise of agriculture and complex societies that would define the Holocene. The last glacial period, also called the Weichselian in northwest Europe, occurred between 115,000 and 11,700 years ago. It was marked by significant climate changes, with temperatures swinging between cold stadial and warmer interstadial periods. These fluctuations were recorded in ice cores from Greenland and sediments from the North Atlantic Ocean. There were also abrupt, intense cold events, known as Heinrich events, during this time. These shifts in climate impacted animal populations and humans, altering migration routes, causing some species to evolve in isolation, and leading to higher extinction rates during the coldest, driest times. The coldest phase of this period, called the last glacial maximum, happened between 26 and 19,000 years ago. During this time, the Earth's ice sheets were at their largest, sea levels were about 120 meters lower than today, and the global climate was generally colder and drier. Greenhouse gas levels, especially carbon dioxide and methane, were much lower, contributing to the cooling. The drop in temperatures, ranging from 4 to 10 degrees lower than pre-industrial levels, was mainly due to the reduced carbon dioxide and the massive ice sheets. Other factors like dust and vegetation changes also played a role in this cooling. After the end of the last glacial maximum, humanity had successfully colonized most of the Earth's habitable regions, showcasing remarkable adaptability and ingenuity. In Eurasia, dense populations thrived in Europe, Asia, and the Middle East. The Fertile Crescent was on the verge of transformative agricultural developments, with evidence of early plant cultivation and animal domestication. Technological and cultural innovations spread widely, facilitated by trade and interaction. In Europe, the landscape during the last glacial maximum was dominated by tundra and steppe, cold environments where animals like horses, reindeer, and mammoths thrived. Human populations, who had arrived in Europe around 45,000 years ago, were concentrated in areas with more favorable climates, like southwest France and the Iberian Peninsula, where they survived the last glacial maximum in refuges. After the ice began to retreat around 19,000 years ago, humans expanded and gave rise to cultures like the Magdalenian. In South Asia, communities along river systems like the Indus and Ganges thrived, utilizing abundant resources and engaging in early forms of plant and animal management. East Asia saw the development of increasingly complex societies, particularly in regions like the Yellow and Yangtze River valleys, which would later become centers of agricultural innovation. In Southeast Asia, humans adapted to dense forests and coastal environments, relying on fishing, hunting, and foraging. Island populations, such as those in what is now Indonesia and the Philippines, demonstrated early maritime skills, facilitating trade and cultural exchange across the region. In Australia and Oceania, humans had established themselves tens of thousands of years earlier, adapting to unique challenges in arid deserts and coastal ecosystems. In the Americas, humans had spread widely across North and South America, navigating diverse environments from icy tundras to tropical forests. Distinct cultures emerged, such as the Clovis in North America, and those associated with fishtail points in South America, reflecting advanced tool-making and survival strategies. These early populations utilized both megafauna and smaller game, while adapting to changing climates. Globally, migration patterns during this period were shaped by coastal routes, river valleys, and land bridges like Beringia, which connected Siberia to Alaska. As the Ice Age ended, melting glaciers raised sea levels, altering landscapes and creating new barriers. This period marked the dawn of the Holocene and set the stage for the Neolithic Revolution, ushering in agriculture, permanent settlements, and the rise of complex societies. The Younger Dryas was a sudden cold period that lasted about 12,000 years, occurring roughly 12,900 to 11,700 years ago. It interrupted the warming trend at the end of the last ice age, and has been studied more than any other climate event in history. While many theories focus on a dramatic event like a massive flood to explain its origin, some scientists argue that the Younger Dryas was just a natural part of the sequence of events during the transition from glacial to warmer periods. One key feature of the Younger Dryas is that it resembles other cold spells in Earth's history, called Dansgaard-Esker events. These events happened during ice ages and were caused by disruptions in the Atlantic Ocean's circulation. During the Younger Dryas, fresh water may have pooled on the ocean's surface, leading to the formation of thick sea ice. But vaster changes in climate meant that fresh water may no longer be obtainable. Most water resources on the planet have been wiped out. This sea ice blocked heat from escaping the ocean, shifted wind patterns, and reflected sunlight away, thereby creating freezing and Siberian-like winters in the North Atlantic region. This cooling affected weather patterns far away, weakening the Asian monsoon and shifting tropical rain belts southward. A popular theory suggests that the Younger Dryas was triggered by a massive release of fresh water from Lake Agassiz, a large glacial lake in North America. This fresh water could have slowed or stopped the ocean currents that normally move warm water north, leading to rapid cooling. Evidence supporting this idea includes a significant drop in the lake's water level and changes in ocean chemistry around the time the Younger Dryas began. However, this theory has faced challenges. Scientists haven't found clear physical evidence of floodwaters flowing from the lake, and the timing of the lake's drainage is uncertain. Some researchers think the cooling might have been caused by a slowdown in ice melting rather than a massive flood. Additionally, ice core records from Greenland show that the start of the Younger Dryas was not as abrupt as other climate shifts, suggesting it might not have been caused by a sudden catastrophe. Interestingly, while the Younger Dryas began with a gradual cooling, its end was extremely fast. Temperatures jumped back to warmer conditions in just 1 to 3 years. This sudden end remains a mystery and highlights how complex and dynamic Earth's climate can be. The Younger Dryas was not an isolated or unusual event, but rather a critical part of the natural sequence that ended the last ice age. Antarctic ice cores reveal that during the deglaciation, warming and rising carbon dioxide levels stalled during a period called the Antarctic Cold Reversal, which lasted from 14,500 to 12,900 years ago. This stalled state needed a major event to restart the climate transition, and the Younger Dryas fulfilled that role. The Younger Dryas shared many similarities with an earlier cold phase known as the Mystery Interval, between 17,500 and 14,500 years ago. Both periods coincided with warming and carbon dioxide releases in Antarctica caused by upwelling in the Southern Ocean. This process brought nutrient-rich, deep sea water to the surface, releasing carbon dioxide into the atmosphere and altering ocean chemistry by mixing older carbon-depleted water with surface waters. Evidence from marine records supports this connection. Sediments show disruptions in ocean circulation, with unusual chemical ratios in the North Atlantic and Central American waters during both the Younger Dryas and the Mystery Interval. These disruptions likely contributed to cooling in the Northern Hemisphere, affecting global climate patterns and slowing the overall warming trend. On land, further evidence links these two events. Cave records in China show weaker monsoon rains during both periods, while normally dry caves in Brazil grew stalagmites, reflecting changes in rainfall. Coastal sediments off Brazil show spikes in river debris, and pollen records in Florida reveal shifts to cooler, drier conditions, with more pine trees. These regional climate changes highlight the global impact of both the Younger Dryas and the Mystery Interval. Unlike smaller, shorter climate shifts like Dansgaard-Oeschger events, the Younger Dryas and the Mystery Interval were part of larger-scale disruptions linked to the end of the Ice Age. This suggests the Younger Dryas was not a random anomaly, but an essential part of the Earth's transition out of glacial conditions. The climate patterns observed during the Younger Dryas are not unique to the last glacial termination. Similar sequences have occurred in previous transitions from glacial to interglacial periods. For example, around 129,000 to 120,000 years ago, during the transition to the Eemian interglacial, there was a brief warming event similar to the Bowling-Allerod phase. The transition that occurred approximately 243,000 to 230,000 years ago, leading to a warmer interglacial period, provides an even clearer example, with equivalence to the Mystery Interval, the Bowling-Allerod warming phase, and the Younger Dryas cold phase. These intervals, spanning several thousand years, illustrate that such cold reversals are recurring features in the deglaciation process. Evidence from Chinese stalagmites and Antarctic ice cores supports this conclusion. Weak Asian monsoon periods during terminations were tied to cold conditions in the North Atlantic, which influenced Southern Ocean warming and carbon dioxide release. These processes contributed significantly to the climate transitions in southern latitudes and the melting of ice sheets in the Northern Hemisphere, reinforcing that such patterns are a natural part of glacial terminations. The data show that weak monsoons and associated cold periods were either prolonged during slow deglaciations or shorter during rapid transitions. These intervals seem to be driven by changes in northern solar insolation and interconnected climatic systems, rather than isolated catastrophic events. For instance, Heinrich events involving massive discharges of icebergs acted as periodic drivers for these transitions, but were not sole determinants of the Younger Dryas. While some argue that a one-time catastrophic event, such as a flood or extraterrestrial impact, might have triggered the Younger Dryas, this view is unnecessary when considering the broader context of the last four terminations. The Younger Dryas caused significant changes in plants and animals, especially in the Northern Hemisphere. This has led researchers to question whether human populations also declined or reorganized during this time. Some studies suggest that the Younger Dryas may have led to changes in population size, how humans used resources like stone for tools, and patterns of human activity. Climate shifts, like the Younger Dryas, can greatly impact ecosystems and human societies. For early humans, these changes could have affected food availability, possibly leading to population bottlenecks, conflicts, or even disease outbreaks. An example of a similar but smaller scale event is the Little Ice Age, 1300 to 1800 BC, which caused crop failures and social unrest in some areas. However, during the Younger Dryas, humans were still hunter-gatherers and not yet farming or living in complex societies, making their responses to climate changes different. Studying the Younger Dryas helps us understand how early humans adapted to major climate changes, which is essential for understanding human history and the impact of future climate changes. The Younger Dryas played a pivotal role in the development of agriculture in Southwest Asia, particularly in the Levant. During this time, the environment became harsher, disrupting the established patterns of life for human groups, who had previously thrived during the warmer and wetter late glacial period. This environmental stress acted as a significant catalyst for the transition from a hunter-gatherer lifestyle to an agricultural one. As the climate turned drier, the vast forests and open forest steppe zones that hunter-gatherers relied on shrank, reducing access to the abundant plant and animal resources. In places like Abu Huraira, there is evidence that people adapted by modifying their plant-gathering techniques in response to these changes. While hunting, especially of species like the Persian gazelle, remained relatively stable, the availability of wild plants began to dwindle, which put pressure on people to find new sources of food. This stress likely prompted the experimentation with domesticating plants and animals, setting the stage for agriculture. Furthermore, the cultural impact of the Younger Dryas cannot be overstated. In areas like the Natufian heartland, larger, more sedentary settlements with advanced tools were abandoned as environmental conditions worsened. As food became scarcer and more difficult to obtain in the traditional ways, people had to adapt by becoming more mobile, resembling lifestyles from earlier, harsher periods. This mobility was likely a response to the diminishing wild resources, driving the need to explore and experiment with new forms of subsistence, such as cultivation. While the Younger Dryas itself may not have been the sole cause of the shift to agriculture, it certainly acted as a powerful trigger. The climatic deterioration forced groups to rethink their subsistence strategies, particularly in the face of shrinking wild resources. In combination with other factors, such as population growth and the increasing trend toward sedentary life, the challenges posed by the Younger Dryas pushed societies toward farming as a more reliable and sustainable way to meet their food needs. Thus, the Younger Dryas played a crucial role in promoting the development of agriculture. The environmental stress it caused, particularly the scarcity of wild plant and animal resources, acted as a catalyst that led human groups in the Levant to seek out new, innovative solutions to feed growing populations. This transition to farming marked a key moment in human history, setting the foundation for the agricultural societies that would shape the future of the region. During the Younger Dryas, human populations across North America experienced a significant drop or major changes in how and where they lived. This cooling period disrupted earlier warming trends, leading to challenges for the people living during that time. Evidence suggests that many communities shrank in size, moved to different areas, or adopted new ways of surviving in response to the colder climate. In North America, spear points used for hunting reveal how people adapted during this period. Before the Younger Dryas, people used a tool type known as Clovis points. As the climate cooled, these tools were replaced by more advanced designs like Folsom and Redstone points. Over time, simpler tools replaced these, reflecting how people adapted to changing conditions. However, the number of tools and evidence of human activity during this time dropped sharply, suggesting fewer people or significant changes in their way of life. In some regions, like the southeastern United States, the decline in population or activity was particularly steep, with fewer tools found at important stone quarries that had been heavily used before. This suggests that either fewer people lived in these areas, or they relied less on these sites during the Younger Dryas. In Alaska, there was an even more dramatic shift. Evidence of human activity completely vanished for about 200 years at the start of this period. Interestingly, after several hundred years, populations began to recover even though the climate remained cold. This shows that people found new ways to adapt, such as moving to more favorable areas, changing their survival strategies, or forming new communities. In other parts of the world, similar patterns were observed, but not everywhere was affected the same way. For example, the Middle East saw its population grow during this time, possibly serving as a refuge for people fleeing harsher climates. Later, around 9,000 years ago, during another period of climate change called the Altithermal, populations declined again, but the reasons for this drop are less clear. Despite these challenges, human populations eventually recovered, showing their ability to adapt to changing climates and environments. During the late glacial warming, humans began returning to northern Central and Northern Europe, regions that had been abandoned during the Ice Age. Radiocarbon dating shows that resettlement started early in this warming period, and people lived in or returned to these areas repeatedly. As the climate warmed, forests grew in northern Europe, allowing hunter-gatherers to spread into areas like southern Scandinavia, where they adapted to forested environments. These early humans used small, portable shelters and stone tools such as arrowheads and scrapers. They hunted various animals, including red deer in the south and moose in the north. Unlike earlier cultures, they produced fewer bone tools and artwork. Their ability to adapt to changing environments with new tools and strategies helped them survive in different landscapes. Around 11,000 years BC, the eruption of the Lachersee volcano in central Germany spread volcanic ash across Central Europe. The eruption had little long-term impact, and hunter-gatherers quickly returned to the region, continuing their way of life. Archaeological evidence from these sites shows that their tools and hunting methods remain the same. During the late glacial warming, two groups of hunter-gatherers emerged, one in the south using smaller tools, and another in the north using larger, specialized tools suited for cold, open landscapes. This distinction highlights how people adapted differently to changing climates. The Younger Dryas, which followed the warming period, caused dramatic climate shifts. Some areas became colder again, with permafrost conditions reappearing in the north, while southern areas stayed milder. The eruption of the Katla volcano in Iceland added to the environmental changes, causing erosion in some areas. These climatic shifts affected both wildlife and human activity. In the north, reindeer were hunted with specialized tools, while in the south, red deer were still the main food source. People continued to adapt by developing new tools, such as fishing hooks and early bows and arrows, to cope with the changing environment. During the Younger Dryas, humans across Europe displayed remarkable resilience and adaptability to harsh climatic conditions. They developed specialized tools such as stone points, scrapers, fishing hooks, and even boats to exploit diverse resources effectively. In Europe, the Ahrensburgian culture, a prehistoric group, lived during the Younger Dryas around 12,000 to 10,000 years ago. This culture is known for its distinctive tools, such as tonged points, and its reliance on hunting large mammals like reindeer. The Ahrensburgian groups are believed to have been highly skilled in seasonal hunting, relying on migratory herds of reindeer that traveled between winter and summer grounds. These groups likely used tools made from reindeer antlers, such as axes, and may have hunted in collaboration with dogs, which helped with hunting and transportation. The Ahrensburgian people's mobility and resourcefulness allowed them to adapt to the harsh climate of the Younger Dryas. Strategic hunting practices like reindeer drives at Stellmore and Schleswig-Holstein and the use of aquatic resources, evidenced by reindeer antler boat fragments, highlight their ingenuity. Communities maximize natural materials, creating tools, jewelry, and symbolic artifacts, like the drilled molar necklace from Remouchamps in Belgium. Archaeological evidence, such as the systematic processing of reindeer carcasses and diverse tool assemblages from sites like Kartstein, Stellmore, and Alt-Duvenstedt, underscores their resourcefulness in enduring long winters and adapting to varied landscapes. These innovations not only ensured survival, but also laid the foundation for future cultural and technological advancements amidst environmental challenges. During the Younger Dryas, there was a possible population decline in Japan. However, pottery use, which began earlier, persisted and resurged in the Holocene, reflecting continuity in social networks and resource use. Hunter-gatherers adapted to environmental changes by shifting to more specialized foraging, exploiting aquatic life and plants, and gradually moving toward sedentary lifestyles, as evidenced by the emergence of shell middens and increased pottery reliance. Younger Dryas was a pivotal period marked by significant climate disruptions that shaped both natural ecosystems and human societies. As one of the most studied climate events, it exemplifies Earth's dynamic climate transitions during glacial terminations. Its global impacts, such as altered ocean circulation, weakened monsoons, and shifts in vegetation, triggered profound adaptations in human behavior. Early hunter-gatherers displayed remarkable resilience, developing new tools, strategies, and social structures to cope with harsh conditions. This period also acted as a catalyst for transformative changes, including the advent of agriculture in the Levant and increased cultural exchange in Europe. The Younger Dryas underscores the interplay between climatic shifts and human ingenuity, offering critical insights into how early societies navigated environmental challenges.